So for this lesson, we're looking at the idea of finding the limit of an expression or a function as we approach either positive or negative infinity. And I start with this generality right here. In general, as a limit approaches either positive or negative infinity of an expression where you have a, where a can be any real number. Label that here. A can be any real number at all. So any real number divided by x as x approaches infinity or positive infinity will always equal 0. And the idea is nothing really new. Essentially, you take a number, divide by something that gets larger and larger and larger, like x is approaching infinity. The larger number that you're dividing by, the smaller your quotient. And while your quotient will never equal 0, if you divide by a massively large number, it gets infinitely close to 0 the larger it gets. And so again, that's what this is really expressing right here. And so in general, anytime a limit as you're approaching infinity equals just some number, some constant, and it could be 0, but just some any other number, then that means there's a horizontal asymptote at that value. So anytime a limit approaches some constant number, essentially anytime the limit converges on some number, that number represents the horizontal asymptote of the function. And you may recall from pre-calculus 12, when dealing with rational functions, a lot of rational functions have horizontal asymptotes, but when dealing with rational functions in pre-calculus 12, we tended to focus on vertical asymptotes. And that's because, to truly understand a horizontal asymptote properly, we need to work with limits. And here we are. All right. So with that said, let's show that this is true. Let's show the limit of sine x over x as x approaches infinity equals 0. Now, hopefully you look at sine x over x as a limit, and that sounds familiar. And we have several times seen the limit as x approaches 0 of sine x over x. That equals 1. And that was proven recently in a lesson using the squeeze theorem. And it came up in one of the first lessons of the unit. But again, this is the limit as x approaches 0. I'm asking the limit as x approaches infinity. Clearly not the same thing. And I'm telling you this equals 0. So how can we show it equals 0? Well, we can use the squeeze theorem, actually, and fairly pleasantly. So I'm going to start with just the sine of x. And we know, regardless of what x is, the sine of x is always between -1 and 1. Well, I'm now going to divide all of these by x. And eventually, I want x to approach infinity. So x is greater than 0. And the reason I'm just stating that is because when dealing with inequalities, when you divide by a negative value, you should switch the inequality around. But eventually, x is going to approach infinity, so I don't need to even worry about that. So I have -1 over x is less than or equal to the sine x over x, which is less than or equal to +1 over x. Well, again, at this point, while I can't directly evaluate the limit as x approaches infinity for sine x over x, I can do that for these other left and right sides of the inequality. And the limit as x approaches infinity of -1 over x has to be 0. And again, that's kind of what was stated right up here. A can be any real number. The limit of any real number divided by x as x approaches infinity or negative infinity always equals 0. In this case, my a value you can think of as being -1. Or even better, I think, just realize you're taking -1 and dividing by massive numbers. You're getting closer and closer to 0. So hopefully you can see how this is going to finish off. And same idea over here. The limit as x approaches infinity of 1 over x is 0, and therefore the limit of sine x over x as x approaches infinity, I know, has been squeezed to be between 0 and 0, and so therefore it must equal 0. All right. That said, I just want to work through a variety of questions like this. Variety of questions where we're approaching limits either approaching infinity or negative infinity. So this next one, the limit's approaching negative infinity. And I'm telling you it equals -3. So how are we going to figure that out? Well, really, it doesn't really matter that it equals -3. Essentially, I'm just giving you the answer. But how can we find the answer? So one thing, if we look at this, as x gets really, really large, or really negative, I should say, there's a whole bunch of stuff going on. In the numerator, that large number is being squared, so it becomes positive. So that large negative number becomes squared, so it becomes positive. But then we find the square root of it. In the denominator, it's not being squared, so it's negative. There's just too much stuff going on for me to see what's happening here. It's definitely more complex than just some constant divided by x. So what tends to be helpful in situations like this is to factor out the largest power from the numerator and the denominator and simplify that out. And essentially what we do is we end up focusing on what really, really matters, because as x approaches infinity or negative infinity, some things like the takeaway 2, the takeaway 4, don't really matter. You know, when you're dealing with massively large or massively negative numbers, subtracting 2, subtracting 4 from it is insignificant. And so we want to really start to focus on what is significant when dealing with these massively large or massively negative numbers. And one way of dealing with that is to factor out the greatest power, like I said, from the numerator and the denominator. So looking at the numerator, even though there's a square root, I'm going to factor out the x squared from inside the radical. So I have 9 minus 2 over x squared, all of this square rooted. And in the denominator, the greatest power of x is just x. So I'll factor out x from the denominator. That leaves me as 1 minus 4 over x. And usually when we talk about taking out factors, we usually try to take out factors so that we have integer values left, not these fractions. But you can really take out a factor, essentially anything you want, aside from 0. OK, what's the usefulness of this? Well, that root x squared, I can simplify that part. And so first, I want to be careful though. First I want to write this as the square root of x squared times the square root of 9 minus 2 over x squared all over x times this. Now you may be tempted to look at this part right here and think this equals x. But keep in mind that's a little bit of an oversimplification. So I want to make a little note right here. So as x approaches infinity, well, actually even before that, I should say, when you have x squared and then square root it, this equals the absolute value of x, not x. And so in this case, though, x is approaching positive infinity. Oh, sorry, negative infinity. Oh, it helps if I read the question. And so therefore, the absolute value of x, as x approaches a massively negative number, is going to be the same as just negative x. And so that square root of x squared, I can simplify down to negative x. If x was approaching positive infinity, I could simplify it down to positive x. If x wasn't approaching any particular number, if it was just x, then I would just leave it as the absolute value of x. But again, we know eventually we're going to find the limit as x approaches a massively negative number. And so with that said, let me write the rest of this out. And now I can cancel out these two factors of x. And now I'm at a point where I can actually evaluate this limit. Yes, it looks messy. Well, it should be a negative up here. And that's because if I actually evaluate the limit now, so I'll write this down, the limit as x approaches negative infinity. If I look at this, I have a bunch of constants, so the 9 and then 1 are just constants. This here, as x approaches infinity or negative infinity, is going to approach 0. That's what the very first part of this lesson. I have a constant divided by x squared. Whether it's divided by x squared or just x, it doesn't really matter. That is going to approach 0. 2 divided by a massively negative number squared is, that 2 is getting broken up into a huge number of groups, so each group must be really, really, really small. Same idea right here. 4 divided by x, as x approaches infinity, that's going to equal 0. So notice, I'm not dividing by 0 or anything like here. I'm not dividing by infinity. This simplifies to minus the square root of 9 minus 0 over 1 minus 0. And so, clean this up. All this comes to negative 3. And so just keep in mind, the idea here is essentially by factoring out the greatest power of x from the numerator and the denominator, I realized what mattered. And in the end, the reason, when I look at this, 2 over x squared or 4 over x, that related back to these terms up here, the minus 2, the minus 4. And like I commented on, after all, those become insignificant as x gets really large or really negative. And that's what this kind of formalizes here. They go to 0, which is insignificant. And keep in mind as well, this little point here, that when you have a value squared and square rooted, it doesn't equal x, it equals the square root of it. Sorry, it equals the absolute value of x. And if we're dealing with positive numbers, those absolute value brackets are doing nothing. If we're dealing with negative values, like we were in this question, the absolute value brackets change the sign. And hence I have the negative in front of the x. We never want to oversimplify and just think that this equals this. Not at this level. Okay? That is correct if we ignore negative numbers, but that's never a good idea to ignore negative numbers. So let's look at this one. Okay, I'm no longer giving you the answer. We just want to evaluate the limit or determine that it does not exist. So how do we approach this? Well, keep in mind there's always many ways, and I'm just trying to show a variety of things here. In this case, you're probably better off taking the expression of 5x plus sine x over x and breaking it up into two fractions to 5x over x plus sine x over x. And that's because I can now cancel this out, and I have a constant. Constants are always nice to deal with, 5 plus sine x over x. So I can find the limit of all of this. As x approaches, this was infinity. And we learned earlier when you're finding the limit of a sum of different functions, you can just look at the limits of each of those separately. So in this case, the limit as x approaches infinity of 5 is just 5. It's always going to be 5. The limit of sine x over x as x approaches infinity. We saw actually several minutes ago that equals 0. Right, that was proven right back here. Right, I stated it equaled 0, and then I proved how it equaled 0. And so in the end, the actual calculation is 5 plus 0, so this equals 5. And let's look at this. Okay, getting more complex. I'm approaching negative infinity. I got some square roots, so I want to be a little bit careful. That said, we did something very similar to this quite recently, so I'm going to do the same idea where I want to factor out the greatest powers of x from the numerator and the denominator. So in the numerator, I take out x squared, and I have 1 plus 4 over x when I take out x squared from the numerator. That said, this is still being square rooted. Okay, in the denominator, take out a factor of just 4. Sorry, x. I don't really care about the 4. Like before, I have that square root of x squared, which is really the same as the absolute value of x. But I'm going to change that in a moment. And at this point, though, so this is true again. X squared square rooted equals the absolute value of x. But in this case, as again, x approaches negative infinity, the absolute value of x is the same as negative x. Exact same idea we saw before. So, maybe I'll just leave it like that, and I'll just write that out the next step, negative x. And so these cancel out, which means I can now evaluate my limit. So I can now evaluate the limit as x approaches negative infinity of this. And hopefully it's quite quick to realize this 4 over x and this 1 over x will approach 0 as x gets infinitely large or infinitely negative. So I'm left with a very simple expression, the square root of 1 over 4. Oh, sorry, I missed my negative, though. It's a negative right there. The x cancels out, not the negative in front of the x. And so I have negative the square root of 1 over 4, or just negative 1/4. I'll show the extra step. And so keep in mind again, with all these examples, in this case, notice as x approaches negative infinity, the function equals negative 1/4, equal the number. That means I know there's a horizontal asymptote at negative 1/4 for this particular function. And this function here had a horizontal asymptote at 5, and this has a horizontal asymptote at negative 3 as we approach these values. And if I think, yeah, this is the last one here. Again, similar. And again, there's always lots of ways of approaching it. This time, I'll start with the same thing. Actually, before I do that, I'm actually going to write this as one big radical, because I am dividing two radicals. So I'm going to write this as just one big radical, the square root of x squared plus 4x. Now, I'm going to factor out the largest power of x in the numerator and the denominator. can cancel out 1x from here and here. And as well, I know as x approaches infinity, both of these that I've highlighted are going to approach 0. So what do I have here? The limit as x approaches infinity of the square root. What do I have left? I have x over 1 plus 0 over 0 plus 1, which really in the end is the limit as x approaches infinity of just the square root of x. So what does this equal? Well, I think the best way of approaching this is just think, what does root x look like as x approaches infinity? And root x is a pretty simple function to visualize, I hope. Root x starts at 0, 0, and it looks like this. And so as x approaches infinity, as the function goes this way, the output just keeps going up forever, and therefore the limit as x approaches infinity must be infinity. It just keeps getting larger forever, which if that seems strange, honestly, the vast majority of functions, if you just made up a function, there's a very, very good chance as x gets really, really, really large, the output's going to get really, really, really large. And any quadratic function that opens up behaves like this. Any line that's going up behaves like this. The larger x gets, the larger the output gets. There's no limit to how large x can get, so there's no limit to how large the output can get. So this is actually really, really common. A few other quick comments. Oops, I didn't mean to erase that much. A few other quick comments. You may have noticed that if I go back here, I could have factored, if I just took a factor of x out of the numerator, would have had x plus 4 divided by 4 plus x. I could have canceled those out right away. There's always multiple ways of approaching it. Just usually as we approach infinity, taking out this greatest power, like I mentioned, can quite often be helpful. Just don't think you have to always do that. There's always different approaches. But that's a very, very common approach as we approach infinity or negative infinity. Either way, of all the examples I've given today, this was the only example that does not have a horizontal asymptote. And that's because of all the examples I looked at today, this is the only example of a limit as we approached infinity or negative infinity where it did not equal a number. It equaled, in this case, it approaches infinity. It just keeps getting infinitely large. Right, so this is the only example that did not have a horizontal asymptote.